Okay, so last class we talked about the fundamental particles basically that make up an atom and how those experiments that got us there. And so we arrive in the early part of the 1900s, say, with this model of the atom that has some organization and some more details about what's going on inside. So you can see, again, and this is an important point in the idea that scientific ideas evolve and they get, not that previous ideas were necessarily wrong, but that they get more correct as time goes on. And we have the protons, neutrons, and electrons. And we have the idea that there are isotopes. Now, on a periodic table, the masses that we see are weighted averages, right? So, for example, silver has two isotopes, 107 and 109. And so the atomic mass of silver is 107.96, and the reason it's is because it's a weighted average of the two isotopes. Now, one of the things that had been in development or been a curiosity for some time in the end of the 19th century, so through the middle end of the 1800s, was this idea of what they called periodicity in compounds, which is that there are groups of compounds, and now we all take this for granted because we use the periodic table, but the periodic table comes from somewhere. And so the idea was that there are compounds that we could group in terms of their behavior. And it turns out that if you sort of line compounds up, you just arrange them in order of their atomic mass, what you find out, actually their atomic number, really, what you find out is that there starts to be these repeating patterns, right? So, for example, lithium, sodium, and potassium all have similar chemical and physical properties. So it's like 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. And what's interesting is that, so the, 3, 11, and 19, but also then beryllium, magnesium, and calcium also have similar properties. So you have this, so periodicity means, there's a regular repeating pattern. And so almost like a sine wave. And so there was a lot of energy put into organizing these things in ways that made sense, that could highlight this. And so Dmitry Mendeleev was the person who really formulated the modern periodic table. And this is really kind of what it looked like when he was working on it in the 1880s, I guess. So the elements that he knew of. And what was really interesting is that his periodic table and all the math that he did with it was so effective that he was able to make some predictions specifically about, I'm pointing at my screen like you guys can see it. So scandium and also gallium and germanium are two in particular, where he was able to predict not only predict their existence, but he was also able to make predictions about their physical and chemical properties and to be pretty good about it. So in particular, gallium and germanium. So Mendeleev predicted, for example, that gallium would have an atomic mass of 68 grams per mole and a density of 6 grams per centimeter cubed. And he was pretty close. And the same thing for germanium. So it's pretty impressive, actually, to have been able to do that. So this is the modern periodic table. We're going to come back to it a lot. It turns out that there's a lot of other stuff that Mendeleev didn't know about that is not explained, but at least how would I say this? Organized. That there's a bunch of other stuff in terms of the the properties of elements and atoms that we can use the periodic table to guide us through. All right, so it becomes pretty important for us. All right, so the interesting thing is that many people saw the end of the 1800s as sort of this golden age for science, and it really was, and in physics in particular. So by that time, there had been all these experiments with electricity. So people knew how to generate electricity, how to do chemical reactions that created electricity, or use electricity to do chemical reactions, which is stuff we saw in NYB. Um, there were, the laws of motion. There was a whole bunch of stuff. So if you had asked, a physicist, many scientists by the end of the 1800s, how are we doing? And they'd be like, we got this. We just have to clean up a few things, and then we've got it all. We'll have, explanations for everything. But it turns out that that was super not the case. So the big problem, where the crack, if you will, in everything came from light. All right. In particular, it came from a phenomenon known as black body radiation. So black body radiation is a phenomenon where you heat stuff up and it emits light. So this could be a burning candle. It could be lava. Ooh, excuse me. It could be the wires in your toaster. Anything that you heat up and then it gives off light. Now, you don't need to know this formula here, okay? Because it's wrong. But there was an this idea that when you heat something up, so here you have the classical theory of a black body, so just something that you heat up, and at 5,000 degrees Kelvin, this is the wave. This is the light that should be emitted. It turns out that it's not true. There's a big difference between a black body at 5,000 in real life versus a black body at 5,000 according to these equations. And the name for this problem is maybe the best name for a science problem ever, which is that it was called the ultraviolet catastrophe. Basically, that the wavelengths that of light that should be emitted were not right, really. Now, this led to a lot more experimenting with light. So, just a little primer on electromagnetic radiation. So, electromagnetic radiation, which is light, is a wave, and it has two components. It has an electric field and a magnetic field that oscillate like a sine wave at 90 degrees and at each other, 90 degrees to each other. So one of the things that was discovered is that all electromagnetic radiation is basically the same. It just differs in terms of the wavelength. So if you go at the very low wavelength, of gamma rays, all the way up to radio waves, they're not different in kind, right? They aren't different things. They just have different wavelengths. And we can only perceive this tiny part of what we call the electromagnetic spectrum here, from say 400 nanometers to about 750 nanometers. That's all the colors of the rainbow. We cannot perceive ultraviolet light or X-ray, infrared, microwave, radio waves. We can't perceive those. We have to use other forms of if you use other things like technology in order to perceive them. So yeah, so Like, for example, there are animals and insects that can see in the ultraviolet or in the infrared, right? We can't. Colors don't really exist, right? They're uh, representations in your brain of ultraviolet light. Um, so there you go. All right. Now it turns out that if we actually go back to here, the photoelectric effect. So this was another experiment done again in the early 1900s, where basically what you have is an electric circuit, but it's open. All right. And so you have a metal plate here and another rod. So you have two terminals inside a vacuum tube. And so when you connect everything, nothing happens because it's an open circuit. But if you shine light on the metal surface, sometimes the circuit closes, which basically means that some light can eject the electrons. They can give the electrons enough energy to leave the metal and close the circuit. Now, what was initially thought was that what would matter is how bright that light is. That would be the important part. In fact, what happens is it turns out that it wasn't the brightness of the light, but rather the color of the light or the wavelength of the light. So, for example, red light does a very poor job of ejecting electrons, but blue light does an excellent job. And what does that tell us is, in fact, that the energy of light is not related to how bright the light is, right? Uh, Rather, it's related to the wavelength. So, light exhibits something called the wave-particle duality, which is sometimes it behaves like a wave, so we can use wave mathematics to understand it. Sometimes it actually behaves like a particle, and so we often refer to light as when we're talking about light, we talk about photons, and we'll talk a little bit more about that idea afterwards. But when light is brighter, it simply means there are more photons reaching a detector or your eye. All right. But the actual energy of light is related to its wavelength. So, for example, this is why ultraviolet light and X-rays are dangerous for us because the light is very high energy. All right. Both of these, and gamma rays too, actually, they're just less common. But all of these wavelengths of light can cause damage to our DNA by interacting with the covalent bonds in our DNA and causing errors or causing damage to the DNA, so that when replication happens, it can cause mutations or errors, which ultimately potentially lead to cancer. At this end of the spectrum up here, the light is not dangerous to us because it can't physically interact with us in the same way at all. As a part of all of this, people were really taking a look at how do light and matter interact with each other. And one of the things that had been known for a while. So the first references to this are in about the 1850s. Nobody can find, as far as I can tell, who did the original work. Most of you have seen, I hope, like the kinds of light bulbs that we have, like in school or in a store, the tube bulbs, like the neon tubes or whatever. If you if you take um, a hydrogen emission lamp, so it's basically a light bulb, but with hydrogen only inside it. All right, and you turn it on, you get this really nice pinkish fuchsia almost light. All right. And then if you pass that light through a prism, you find out that it's made up of one, two, three, four, and well, actually five actual lines. There's only five different wavelengths. It's not all the colors of the rainbow that hydrogen emits when you give it some extra energy. It's just these ones. This was first described mathematically by two people, Rydberg and Balmer, separately. This constant here is known as the Rydberg constant, and sometimes this is referred to as the Rydberg equation. What's interesting is he was able just to sort of take these numbers and figure out a mathematical relationship. So the numbers for the wavelengths of light here, and figure out this mathematical relationship. And what was required was an integer. N is an integer greater than, in this case, greater than 2. Now, that in and of itself, just from pure mathematics, is quite an achievement, because if I just gave you a random set of numbers and asked you or an apparently random set of numbers and asked you to find the mathematical relationship, you'd be hard pressed to do it. With all of the discussion that was in the, I guess, in the scientific air at the time regarding how atoms were organized inside, along with the ultraviolet catastrophe, Niels Bohr was able to organize this and say, well, hey, you know what? Maybe this Rydberg equation has physical significance. So that if we go back to the Rutherford model of the atom, what do we have? We have a nucleus that's organized, and then electrons, but we don't know anything about them. If electrons are anywhere in that space, then when they move around, really, they should be able to absorb or emit any colors of light. Bohr suggested is, well, what if these wavelengths of light actually tell us about where the electrons are in space around the nucleus? And he developed what's known as, well, the Bohr model. It's sometimes called the planetary model of the atom. And you have the nucleus here in the middle, and then you have orbits around the nucleus. And when an electron moves between these different orbits, it gives off light, right? So for example, what would happen in the light bulb is you add electricity. So normally the hydrogen electron is here in the nucleus, or sorry, in its lowest energy state. All right, what we call the ground state. And when we add energy, so in the light bulb, we're adding energy by adding electricity. So when we add energy, what happens is the electron moves away from the nucleus, and it can move anywhere within reason. It means it can't just move to any distance from the nucleus. It can move to one of these other higher energy levels, and they're called higher energy. Why? Because they're further away from the nucleus. It requires energy to get them away. So this is, if you think about just electrostatics, right? So opposite charges attract each other, right? Because the nucleus is positive and the electron is negative. So they attract each other. And if I want to move them away from each other, what do I have to do? I have to add energy. So this is by adding energy, this electron can move away. It could move, I'm showing it moving up to this n equals 5 level, this level, but in fact, it could move anywhere. And then, so it's all excited, and then it relaxes, it falls back down. And we're going to see it actually can take lots of different ways down. But it turns out that when it goes from wherever it is and ends up, at least temporarily, at n equals 2, it emits light that we can perceive, right? It doesn't stay at n equals 2. It would fall back down or relax back down to n equals 1, but we can't perceive that transition. All right. It took until later with the development of ultraviolet and infrared detectors for us to be able to verify those. So this model of the atom is the Bohr model or the planetary model, and most of you, this is probably where you stopped in terms of elaborating things. The way you can think about it as a sort of mental model is a bit like, for us, this is the same as gravity, right? So I am attracted to the floor by gravity. If I want to get to a higher energy level or move away from the floor, I jump. And I can't stay up in the air. I fall back down, right? And now what happens is when I fall back down, the energy that I give off is kinetic energy, or it's the energy that I have is kinetic energy. But in the case of electrons, they give off light. The electron absorbs energy from some source that it has to be given. When it does that, it can move away from the nucleus, and then it doesn't stay there very long because it's like it jumped up into the air, and then what happens? It falls back down to the lower energy. The Bohr model gives us a way of understanding a bunch of new things, and it gives us a much more detailed picture of what's going on inside of an atom. We now have an organized nucleus, and now we have some degree of organization for electrons, right? So we've got this method where we can explain what is happening in terms of why, for example, hydrogen only emits these colors of light. So there's another equation that I didn't show you, which is the equation that relates energy and light, and that's on the left. That's E equals hc on lambda. So h is the Planck constant, c is the speed of light, and the lambda is the wavelength in meters. These are always in meters. Right, so what happens? N equals 1 is what's referred to as the ground state for hydrogen. It's the lowest energy level. So the electron can absorb energy and then emit energy as it falls back down. This is a sort of a better picture of the whole hydrogen spectrum, which is that if you give an electron enough energy, it can go into some infinite energy level. That's like so it leaves, and that would be making a hydrogen ion, H+. Now you have to remember that these things can happen by chemical reaction as well. When electrons fall or relax and they end up back at n equals 1, the light emitted is in the ultraviolet. When they fall and arrive at n equals 2, that's visible, and then if they arrive at n equals 3, that is infrared. Now, the thing to realize is that not only are these direct paths, but combinations, the electrons always end up at n equals 1. They always fall back to their lowest energy. And so, for example, an electron, you can imagine, so this electron here, it could start its path by going to here, right, to n equals 3, but then it would fall, say, to n equals 2, and then all the way to n equals 1. So in its return to the ground state, this electron here would emit 3 photons, right? It would emit light 3 times, once in the infrared, once in the visible, and once in the ultraviolet. You can't actually know, like if you only have one electron that is excited from one hydrogen atom, you can't predict which path it will take to get back down to the ground state. However, in, say, a hydrogen discharge lamp, you have enough hydrogen atoms, so therefore enough electrons, so that just statistically speaking, all of the paths occur, right? Because you're talking about, gazillions of hydrogen atoms. This is an emission spectrum on top of sort of just the rainbow. This is the reverse. This is what's called an absorption spectrum. And I think this is for oxygen. I'm not 100% sure. But you may have heard, like if you follow, news about astronomy and cosmology, and they, make announcements about, oh, we discovered these planets, and they have, this kind of gas in their atmosphere, or for example, even things in planets in our own solar system, we're fairly certain have certain types of gases in their atmosphere, like say Venus or some of the moons of Jupiter and Saturn. Well, here's the thing. What actually happens is, based on the light that hits those planets from the sun or whichever star, we can tell which wavelengths of light are absorbed by the atmosphere and how much they're absorbed. And you can actually figure out then which elements are present in the atmosphere, and then ultimately even which molecules are present in the atmosphere of planets elsewhere in the solar system or in other solar systems. So it's actually pretty neat. There are two general equations for making calculations with the hydrogen emission spectrum. The top one here, which allows us to calculate wavelengths. This one allows us to calculate energy. Like Dalton, Bohr was right in general, but there are some specifics that are sorely lacking in his model. All right. So the first limitation of the Bohr model was that he could only get it to work for hydrogen. Right. So remember that Bohr built his model based on the emission spectrum of hydrogen. Now, if these rules are, if this model or theory is any good, it should be broadly applicable. It shouldn't only work for hydrogen. It should be able to either interpret or predict the emission spectra of other elements. Now, when we think about the difference between, say, elements, the first thing that hopefully pops into your head is that they have different numbers of protons, right? So, and therefore also different numbers of electrons. So, for example, if I want to predict, say, the emission spectrum of helium instead of hydrogen, right? Well, helium has 2 protons, right? Now, that means so that the charge on the nucleus is +2 in helium. And that means that the electrons in helium are more strongly attracted to the helium nucleus than in hydrogen. So that is a factor that needs to be taken into account. And so that is where the introduction of this comes into play, right? This is the atomic number. So for hydrogen, it's 1, so it doesn't matter. So for helium, that means we would put a 2 in there, and hopefully it would work. The problem with the Bohr model is that it doesn't. It only works for hydrogen, right? The Bohr model works for hydrogen, and the other thing it works for is other, what we would call one electron species. The Bohr model doesn't work for helium, but it does work for helium plus, right? Because it works 2 protons, 2 electrons. Helium plus has 2 protons and 1 electrons, all right? So this only works for 1 electron species. As soon as we introduce a second electron, the model goes out the window. It doesn't work at all. All right, so this is a huge problem, and this is why we have essentially discarded the Bohr model, because it doesn't work. There are parts of the Bohr model that have pointed us to our modern understanding of atoms. This is one of my favorite science quotes. You have to remember that it's from about 1927, so the use of the term queer should be taken in context, right? It means weird, strange. So my own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. And I think this is true. Some of you might have done this experiment in high school. It's what we call the double slit experiment, where if you take light and you shine it on a piece of cardboard that has 2 holes in it, you get what's called an interference pattern. It looks like this, right? So light moves in waves, and if you could see this actually if you have like a swimming pool or a pond or a lake, and you drop 2 rocks in at the same time, you get constructive and destructive interference. So where the waves are what we call out of phase, right? Where the maximum of one wave meets the minimum of the other, they cancel each other out, and you get dark spots. In the opposite case, when the maxima line up, you get what's called constructive interference. So, for example, this is X-ray. This is a pattern of X-ray diffraction. All right. So, actually, one of the really cool things that we can do with molecules is we can shine. So, when you have covalent bonds, the nuclei between the atoms actually act like little slits, and so the X-rays diffract, and so you can actually look at these patterns and run them through a computer and figure out how far apart nearby nuclei are, and then how far apart bonds are, how long chemical bonds are. This is something that will come up a little later on. So now we're getting to 1920s, I guess. We have a whole bunch of new equations, right? You have the equations for light and energy, and you also have Einstein's famous equation for matter and energy and the speed of light. Now, the interesting thing is both of these things are equal to energy, right? And you can, instead of putting, because c just refers to the speed, we're light. So we could say, well, instead of that, what if we said the energy of a moving object is mv squared? And that's kind of true normally, right? This is very similar to the equation for kinetic energy. And what if we did this crazy thing where we said, well, instead of the speed of light, what if we looked at a wavelength? Now, that seems really weird, but there is an Italian physicist named Louis de Broglie. It's spelt de Broglie, but French Piedmontese, and the pronunciation is really weird. It also doesn't matter, the pronunciation. He said, well, what if I combine all of this stuff on this side and say, well, for a moving object, I could calculate an associated wavelength. Now, who cares, right? This seems ridiculous because if I look at, say, a moving baseball, now everybody has a rough idea in their head about the size of a baseball. So a moving baseball, 13 meters per second, that's pretty fast. It has a wavelength of 10 to the minus 34 meters. So even if this baseball has some sort of wave associated with it, it's so small relative to the actual baseball that who cares? It doesn't make any sense. It doesn't mean anything. But it turns out that for other particles, this might matter. So, for example, an electron, which has a mass of 10 to the minus 31 kilos, and now you have something moving very fast, close to the speed of light. The wavelength associated with this, just mathematically, is on the order of 10 to the minus 10. But if you remember, the diameter of an atom is also about 1 times 10 to the minus 10 meters. So the wave that we calculate that's associated with this electron is roughly the same size as the environment the electron lives in. And that means we can't necessarily discount this calculation. And this is bolstered by a really crazy experiment. Now, if we assume that electrons are little bits of matter, little marbles, right? I would expect that if I shot electrons through this double slit, I would get, all the ones that don't go through are going to hit the screen, and then the other ones, and I'm just going to get 2 bright spots. But what actually happens is I get a diffraction pattern or an interference pattern. So electrons, which have a mass and have measurable kinetic energy, for example, turns out that under certain circumstances can behave like waves. The first thing was, well, how do we figure this out? What does this mean? How are electrons interfering with each other? Maybe when they go through, they're bouncing off each other, and that creates the thing. But what happens is actually if you put a detector, so a laser beam can act as a detector. Here, they go back to behaving as if they were particles. So they don't follow any rules that we like. I mentioned earlier that light has what we call wave-particle duality. which means that sometimes it behaves like a particle and sometimes it behaves like a wave. And guess what? So do electrons and neutrons and protons, and in fact, even really big molecules sometimes, depending on the circumstance. So electrons actually can behave like waves. So this idea that we can calculate a wave function or a wavelength related to a, a moving electron is not insignificant, because in real life, under certain experimental conditions, electrons actually behave as if they're waves. Out of most of this experimental work came a few different things. One of them, importantly, is something I'm sure you've heard about, but it's called the Heisenberg uncertainty principle. And basically, the Heisenberg uncertainty principle says we've got position and momentum, and those have to be the product of those has to be, there's a hard limit, if you will, to how much to this product. So, for example, if I know a lot about the momentum of a particle, I can only know a very little about the position of the particle. Or if I know a lot about the position of the particle, I can only know a little bit about the momentum. We're entering now into what we call the quantum mechanical model of the atom. You basically have to give up on any intuitive understanding or having a good mental model of how this works, because evolutionarily our brains can't handle it. We've evolved to have a really good understanding of things that are, say, as small as the thickness of a hair, up to the size of a mountain. Things that move much, much slower than the speed of light. We can imagine those things. But things that are significantly smaller or moving close to the speed of light, we don't have mental models. And I don't even know that our brains can create real good mental models of them. It's really just, we have to sort of stick to the mathematical models. That's what works for me anyway, because it's so weird. In this version of the experiment, there are a series of potential outcomes. An electron is going through both slits, or one and the other, interfering with itself. There's all kinds of crazy stuff, because in fact, if you do the experiment like this and you send one electron at a time, you still get the interference pattern. But as soon as you try and observe, you go back to behaving like a particle. So basically, what we generally try and do when it comes to these types of particles is we'll settle for a little bit of both. We'll go with a little bit of understanding of position and a little bit of understanding of momentum, and that is going to have to be good enough. We live in a Newtonian world. The scale of our existence, and therefore the scale of matter that our brains have evolved to understand, follows Newtonian mechanics. I can know both the position and the momentum of a moving object with essentially infinite detail. One has nothing to do with the other, right? You did all of this in Sec 5 physics or in your mechanics, right? You throw a ball and you follow the movement of that ball. You can know exactly where that ball is at every second or fraction of a second along the path. You can know its position and you can know its momentum, and all of that works perfectly. That doesn't apply to really small objects moving close to the speed of light. That's it. Newtonian mechanics don't work at this scale. There we go. All right, so back to quantum mechanics. So just a reminder, how we get here is we arrive at the Bohr model because the Bohr and people at the time were looking for a way to tie together things like the hydrogen emission spectrum with new experiments involving light and things like that. And so Bohr comes up with this planetary model that does a great job for hydrogen. The problem is ultimately that it only works for hydrogen or other species with one electron, which really there aren't very many, right? So it works for hydrogen. It also works for helium plus, but not helium. It works for lithium 2 plus, but not lithium, and so on. So a model that isn't very good at explaining things isn't a very good model. This is a very limited version of the model. The reason we spend so much time on it is because after this, the math goes bonkers. All right. So, but conceptually, this is important because what Bohr and the people he was working with at the time, people like Heisenberg and Max Planck, they were able to bring out this idea that energy is quantized. All right. That's where the term quantum mechanics comes from. And what does that mean? It means energy is allowed to be absorbed or emitted by matter in small amounts, almost like climbing a staircase or going down a staircase. So we talked a little bit about the wave-particle duality. The problem ultimately comes from the fact that we are dealing with very, very small particles moving very close to the speed of light, and that we're trying to treat them like objects that obey Newton's laws of motion, and they don't. So the experiments that show the wave particle duality for electrons, right? So that sometimes, and again, this is sometimes the wave particle duality, right? Sometimes people think that it means sometimes an electron is a particle and sometimes an electron is a wave. That's not true, right? What an electron actually is, I don't know. What we can say is that sometimes we can describe an electron's behavior like a particle, and sometimes we can describe an electron's behavior like a wave. That's it. It doesn't tell us really anything necessarily about the fundamental nature of an electron. It just tells us how we can describe its behavior. All right. And so the realization that if we do these de Broglie calculations about the size of a wave associated with a moving electron, we realize that it's about the same size as the environment that an electron lives in. So we can't discount it. And maybe there's something about wave mathematics that makes things more accessible. And so that's in fact how this works. But we realize when we're dealing with waves that we have to give up on Newtonian mechanics, ultimately. Go back to these equations. If you think about what this equation is modeling, what's it modeling? It's modeling the difference between the energy levels against this bit here. And this bit here represents the attraction to the nucleus. And if we think about a one electron species, well, what do we have? We have the one electron and we have its attraction to the nucleus. And that's it. Right? So that's the only interaction. What happens when I add another electron to the system? What other types of physical interactions are going on? They repel each other. So if I have nucleus here, and then I have an electron around it, so here I have an attraction. And in terms of dealing with the mathematics, we see that algebra does the trick, right? So the Bohr equation is just a straight up algebraic equation, and it works fine. If I introduce another electron, it's also got an attraction, but now it's got a repulsion here. And no matter what anyone tried to do to the Bohr equation, the first thought was not, we're just going to, oh, it doesn't work, so we're just going to chuck the whole thing. What people tried to do is, well, is there some other constant or variable that we can introduce into this equation to account for this repulsion? And the thing is that whatever people tried to do, it didn't work, right? There's no way they could model the energy changes in something even as simple as helium. And in fact, becomes what's known as a three-body problem. It turns out that basically using Newtonian mechanics and straightforward algebra fails miserably. What we have to do is actually say we're going to give up on knowing exactly the position or the momentum of an electron in space. We're going to settle for knowing a little bit of both, really. That's the whole idea of the Heisenberg uncertainty principle. So, for example, the idea is with Newtonian mechanics, if we want to know where this hockey puck is going, well, if you know the position of the puck, the angle at which the stick hits it, and how hard the stick hits it, and the friction and the air resistance, you can plot exactly where that puck is going. What it turns out is that when we're dealing with particles that are very small and moving close to the speed of light, we can't do that. All we can do is we can say, well, this is where it is. This is more or less where it's going to end up. And this cloud of potential is where the probability distribution of its trajectory. Basically, the idea is that we can actually treat a moving electron, in this case, we're just going to focus on electron, a moving electron as if it is a wave, basically what we would call a standing wave, so like a vibrating string. And the mathematics for wave functions. So you guys have been introduced to the mathematics of waves, right? So sine functions, cosine functions, those are wave functions, two-dimensional wave functions. There are three-dimensional wave functions too. And if you treat now a sine wave, for example, is an infinite wave. It proceeds along its axis infinitely. But there are mathematical functions for standing waves. So you can imagine, for example, a vibrating guitar string is a standing wave, right? The string is fixed at either end and it vibrates inside, and there are mathematical equations for modeling that, all right? And not just a string, but a three-dimensional thing. And it turns out that those are a lot better at modeling a system for the energy of an electron. And we get to what appears on the surface to be a much simpler equation. This is the Schrodinger equation. And so psi here, the Greek letter psi, that is the symbol for a wave function. So the wave function of the electron. And so what it says is the energy of the wave function is equal to the h psi. Now, it's not E times psi is equal to h times psi. That would be awesome and really easy to handle. What this says is the energy of the wave function is equal to the Hamiltonian operator of the wave function. Now, an operator is something so a simple version of an operator might be an integral or a derivative, right? Those do a thing to an equation. The Hamiltonian is the same, except it looks like this. Okay. Now, a couple things. You don't need to do this. You don't even need to know what this equation looks like. And you don't need to solve it, because guess what? Nobody can. All right. The best we can arrive at are approximations. But this is what the Schrodinger equation looks like. Yikes. However, what we are able to withdraw from this is some stuff that we can simplify in order to understand relative energy levels for different electrons in atoms. Basically, what we go from is this simple idea that we need one of these numbers, one of these integers, to describe the energy of an electron, to needing a few more. And what we actually need are initially 3 of these integers in order to describe the energy of an electron. And we call these numbers quantum numbers. And basically what quantum numbers give us is an address that we can use in order to find an electron in an atom and understand its energy relative to other electrons in that atom. So there's 3 main quantum numbers. There's the one we've already seen, n, which is called the principal quantum number, and this represents the energy level of the electron. And basically, what the way I want you to sort of imagine this in your head, all right, is that the n tells us how big the wave function is, like how far from the nucleus does it spread. But then we also need these other numbers. And the thing is that the two subsequent quantum numbers depend on the first one. All right, the L quantum number tells us what is the shape of the wave function, right? What form does it have? And we'll see there's a few different ones, or you should have already seen that there's a few different ones. Right? What form does the wave function have? And depending on the value of n, there are different allowed shapes. So for example, in the lowest energy sublevel, n equals 1, the only possible value for L is 0, right? Because the allowed values for L are from 0 up to n minus 1. And so that's it. So in this case, it's just 0. And it tells us the shape, all right? And we'll get to what those shapes are. The ML tells us the number of possible orientations that exist for the orbitals. And it turns out that each orientation is its own wave function. Now, what happens is these new wave functions, we stop calling them orbits, right? So in the Bohr model, they're called orbits. But what happens is we stop calling them orbits and we start calling them orbitals. And the reason we use orbitals is it's a nod to the Bohr model, because really the Bohr model, even though, again, it's wrong in many ways, it's a big leap forward compared to what happened before it. There are other energy levels further away, and each of them has more and more what we call orbitals inside it. First of all, the way we talk about different orbitals, because it's all numbers, typically we don't talk too much about the ML one if we don't absolutely have to, and we'll see why that is. So you're often going to see orbitals referred to with a number and then a letter. The number always refers to the value of n, the principal quantum number, and the letter always refers to the value of L. And this is the way they're tied together. When the value of L is 0, we call it an s orbital. When it's 1, it's a p orbital. When it's 2, it's a d orbital. When it's 3, it's an f orbital. And then actually there's no more. All right, there are no atoms with enough electrons, and you'll see how this works, to have more than f electrons. We always think about these things as we're working from lowest energy to higher energy. So the smallest possible value of n is 1. And if n is equal to 1, L is only allowed to be equal to 0. So this would be the 1s orbital. A 1s orbital is spherical. It doesn't mean that the electron is a sphere. What it means is that the wave function that is associated with this electron is roughly spherical, or the probability density for the wave function, which is the wave function squared, is spherical. And it's probably, this one is probably better. I like these ones, the radial. So we often think about total radial probability, which again, we have to use inadequate mental models. Basically, what this is where is the probability density for the electron, which you could kind of think as the space where that electron is most likely to exist, except that it's not really a particle. It's a sphere, and so the probability density, the radial probability at the nucleus is 0, right? And then it has a maximum out here, and then it sort of fades away, but there's no hard cutoff. We can see that when we're thinking about the electron as a particle, it's roughly 53 picometers. Picometers are 10 to the minus 12 meters, but obviously it's not like the Bohr orbit where it's like, this is the distance exactly. There is variability, right? It is a distribution. So there's some other weird stuff that comes up in the mathematics of waves. So I mentioned that we can think of the wave functions as as standing waves or vibrating strings. And one of the things that shows up in wave functions are what we call nodes, right? And if this is the 0, and if you forgive my poor drawing skills, if that red line represents the 0 of the function on this graph, right? The spots where the wave function crosses the origin or crosses 0 those are referred to as nodes. Now, why does this matter? Well, because when we get to larger orbitals, so where, say, the 2s orbital, right, where n equals 2 and L equals 0, what happens is the probability looks like this, where on average, the probability density for the electron is further away from the nucleus. And that makes sense, right, because we have n equals 2, right? And remember that the value of n is sort of overall the size of the orbital. But there is a little bit of probability density here very close to the nucleus. In fact, that overlaps with the 1s orbital. And in between, the the probability density hits 0. Now, if you think about the electron as a particle, that doesn't make sense. Like, well, how does it get from here to here without going through that space? But again, remember, if you think of the electron as a vibrating string-ish, having a node makes more sense. It's just a node in the wave function. Right? And as we go up, you can see, so this is a 3s orbital, which on average is bigger than a 2s, but also has nodes and spots where the density is much, much closer to the nucleus. All right, the terminology that's used is that the wave function penetrates close to the nucleus. This is going to be important a little later on. So s orbitals are spherical. And as the value of n gets higher, then they get bigger, but they also have these weird little nodes in them. Starting at n equals 2, the allowed values of L are 0 and 1. So this one, this would represent a 2s orbital. This one here, this represents a 2p orbital, but we know, right, so if n equals 2, L equals 1, well, now this brings in ml, and there are 3 allowed values of ml, -1, 0, and 1, which means that there are 3 different orientations of a p orbital. And it turns out that each of them falls on one of the Cartesian axes, x, y, and z. And the shape, it looks kind of like 2 balloons tied together. When I draw a p orbital, right, it looks something like that. And that's like these bubbles are called lobes, and they are supposed to be the same size, but I'm not very good at drawing. The 3 different orientations fall along the Cartesian axis. So we have, this one looks like the px orbital, this is the pz orbital, and this is the py orbital. This is only by convention because atoms move in space all the time, but typically the px is given L is equal to -1, the py is given L is equal to 0, and this one here is L is equal to 1. So the 3 different p orbitals have roughly the same probability distribution in terms of distance from the nucleus. That's just their orientations are different. As we get bigger, we kind of have the same thing. It's just a bigger version of the p orbital. There are also nodes inside them. I'm not super concerned about your understanding of nodes. It's really the shapes of s orbitals, the shapes of p orbitals, and how the quantum numbers tie together. That's important, right? In terms of what I might ask of you, like on a test or a final exam, the ability to sketch an s orbital or a p orbital is something I could ask of you. And look, this is kind of what I'm at. This is as good as you need to get with your drawings. One thing I might ask, for example, is to sketch 2 different orbitals with different quantum numbers. And so you being able to know relative sizing and stuff like that, that would be important. D orbitals, there are 5 possible d orbitals, right? Because if we have L is equal to 2, ml, it can be equal to -2, -1, 0, 1, and 2, right? You don't need to know these ones. This is my favorite d orbital. This happens to have this is known as dz squared. You don't need to know that really, but I always think of this as a p orbital with a donut. and I like donuts. So there you go. So there are 5 possible d orbitals, and there are 7 possible f orbitals, and these ones are really weird. There's a few things that are important. So first of all, why do we consider atoms spherical? So in fact, when we do advanced microscopy techniques that allow us to see individual atoms, like things like what we call electron force, atomic force microscopy, or scanning tunneling microscopy, atoms look spherical, even at a very high resolution. And the reason actually is that for each energy level, the s orbital, even though it's the lowest energy, is actually the largest of those orbitals. So for example, if we look at the n equals 2 level, the 2s orbital is slightly larger than the 2p orbital. So the outside is spherical. What we're going to start seeing is that the arrangement of electrons in these orbitals helps us understand a whole bunch of stuff about the behavior of the atoms. And this all also ties back to the periodic table. So for example, it turns out that each orbital, and when I talk about each orbital, I mean each of these is a distinct orbital. Each orbital can hold 2 electrons. The reason this gets complicated is when we have a hydrogen atom with only 1 electron, this looks like the very simple energy level diagrams that we drew for, or that I drew anyway, for hydrogen. The n equals 2 are all the same energy. The term we use is degenerate. Degeneracy means they have the same energy. All the 2s are the same, all the 3s are the same, and so on. When we add that extra electron, we get what's called sublevel splitting. In the n equals 1, there's only the one possible orbital, so that doesn't change. As soon as we get to n equals 2, what happens? Well, in n equals 2, we have 2 possibilities. We have 2s and the 3 different 2p orbitals, but now they are split. The 2s orbital is lower in energy than the 2p orbital. And they keep splitting, and it gets a little messy. The splitting is not always clear cut as we get further and further away from the nucleus. The last thing I want to introduce today, so like I said, it turns out, for example, that each of these boxes or lines represents an orbital, and each orbital can hold 2 electrons. Now, it turns out that if you think about it, if you have 2 electrons existing in the same space or being described by ultimately the same wave function, we still have this problem of them repelling each other. And it turns out that there is another property that is often referred to as spin, even though electrons don't really spin, but it has to do with essentially magnetic fields. So there is a 4th quantum number that is denoted as ms. All right, and it has a value. It can either be plus a half or minus a half. And the value of ms is actually, so you know how so we have the principal quantum number, and then we have L and ML, and each of those is, the other 2 are tied to the number that came before it, right? They depend on the number that came before it. MS is independent of those. The only thing is that when we have 2 electrons in the same orbital, they have to have opposite spin quantum numbers. We'll give you the example of helium, right? So this is an important one. The Pauli exclusion principle says that no 2 electrons, and it should be no 2 electrons in an atom, can have the same 4 quantum numbers. So, for example, helium has 2 electrons. So if I draw my energy level diagram, 1, so this is n equals 1, so this would be my 1s orbital. Then I have up here n equals 2, so this would be my 2s, and my 3 different 2p orbitals, and then so on. Well, each orbital, it turns out, can hold 2 electrons. The way we denote in these drawings electrons in orbitals is by arrows with half a head. An arrow like this, and we take away half of it. When we are trying to figure out how electrons are arranged in atoms, because that's the whole point of this, is to try and understand how electrons are arranged in atoms, I have this, That's the first electron. Now, this electron here, I'm going to call this one electron A. Right? Electron A then, for this one, n equals 1, because that's the lowest possibility. L is equal to 0. ML is also equal to 0. And then MS is going to be equal to plus a half. And we always, the first electron that goes into an orbital is given, we draw it with an up, and it's given the spin quantum number of plus a half. Now, the other electron still goes into this orbital, but it has to have the opposite spin. And the spin actually is a reference to the magnetic field of the electron. So in order to compensate for electrons existing in the same physical space and both of them being negative, they have opposite magnetic fields. So the repulsion is a little bit decreased. So this would be electron B, and it's still in n equals 1, right? It's still in the 1s. So the first three quantum numbers are the same, but the spin has to be opposite, minus a half. So the four quantum numbers then give each electron in an atom a unique address where we can identify it and talk about its energy.